what is a preferential ballot election? Well, let me remind you that each voter gets to specify not only their first choice candidate, A, B, C, or D, but also their second choice, their third choice, and their fourth choice. So, for example, imagine you have an election for governor, and it's between Anderson, Brown, Davis, and Chang. Well, you might have one voter, voter number 1, whose first choice is candidate A, second choice is B, third choice is D, and fourth choice is candidate C. But then again, you might have another voter who has preferences this way, and then a third voter who has yet, again, a different set of preferences, and of course you're probably going to have many, many voters. And one of the most fundamental things you can do with this data is to create what's called the margin of victory matrix. We simply want to look at all pairwise matchups. So for example, you can ask the question, what if it was just A versus B who won this election? Or let's say B versus D even. So in this case, we can see that B versus D, we see that B beats D here, but then D beats B here, and then D beats B there. So we already have one vote, B over D, and then we have 2 more votes for D over B. So we can count up the number of voters that prefer B over D, and maybe that's 25 voters. And on the other hand, how many voters prefer D over B? And maybe that's only 20 voters. In total, then, we can see that B beats D by 5 votes. So 25 minus 20 is equal to 5. And this is the number that's in the margin of victory matrix here. B beats D by 5 votes. So it's the number of people that like B more than D minus the number of people that like D more than B. The key point is that these numbers here are simply the results from head-to-head matchups, which is possible to determine for a preferential ballot election. That's one thing that's really great about a preferential ballot election is that you're getting a lot of information from each of the voters. And so what we should recognize is that when you look at all these votes, there's really a lot of different ways people can vote, and it's not all obvious who won the election. And to define who won the election, we need to create data like this margin of victory matrix, and then define a method that's based on this data. So there are a number of methods that use this margin of victory matrix, and before I discuss them, notice that we can take this information and look at it more pictorially with this picture above it. And instead of having in row A, column B, a 20, and in row B, column A, a negative 20, which necessarily has to be the opposite sign, because if A beats B by 20 votes, B loses to A by 20 votes. We can simply say, draw an arrow from A to B, and say that A beats B by 20 votes. And then also B beats C by 30 votes, because we have a 30 right here, and so on. B beats D by 5 votes, because we have a 5 right there, and a minus 5 right there. Okay, so this is a nice way to look at the information as well. So now, how are we going to use this information to determine the winner of a preferential ballot election? Well, it would be kind of nice if there was one candidate that beat everyone else in a head-to-head matchup. Unfortunately, in this picture, you can see that's not true. Everybody loses to somebody. A loses to both C and D. B loses to A. C loses to B. And D loses to both B and C. So now, who should win this election? It's an interesting question. Well, ranked pairs is an algorithm for defining who won the preferential ballot election. And as I said, it's my favorite algorithm, so I'll describe at the end of the video. But first, how does it work exactly? Okay, so the way ranked pairs works is you take all these green numbers here and you rank them based on the largest first. So the largest number, I believe, is a 30, right? And the second largest is a 25. So I can do 30, 25. Then the next largest number is a 20, and then a 15, then a 10, and then a 5, which conveniently I've made all multiples of 5 just for simplicity. And then you need to write down what each number represents. So 30 votes is the largest number, and this means this is the strongest preference that the voters have. The voters, the clearest preference is between B and C. So we can say that B defeats C, which we're going to denote by a greater than sign. B is greater than C. Okay, if you think of B and C as algebraic variables or something. B defeats C by 30 votes. Now the second strongest preference by the voters is a 25, which says that C defeats A. So the voters are pretty sure they like B more than C and then C more than A. Now the third strongest preference is the 20. That's that A defeats B. So we'll write A bigger than B. And we just go down the list and write down all these inequalities. 15 is that D beats A. 10 is that C beats D. And 5 is that B beats D. Now the way ranked pairs works is we simply try to enforce these inequalities one at a time, starting with the strongest. So for example, we can see that B must beat C, so we put a check mark by it, and then we say that B is bigger than C. Down here, this is the summary of our results. And then we ask the question, can we enforce this second preference? Is it compatible with what we've got so far? And the answer is yes. We can still have B bigger than C and C bigger than A at the same time. There's no contradictions, so we put an A there. And then we ask the question, can we have this inequality A bigger than B if we already have B bigger than C and C bigger than A? And the answer is no, we can't, right? Because if you think of them as variables, if B is bigger than C and C is bigger than A, by transitivity, it means B is bigger than A. So we can't have A bigger than B. That contradicts B bigger than A. So we have to put an X mark by this one. We cannot enforce that preference. Then it says that D is bigger than A. So we'll put another inequality here. D is bigger than A. But we don't know the order of D with respect to B and C at this point. But we can certainly have this inequality. And then it says, well, C has to beat D. Okay, so that means D is going to have to be placed between C and A here. So that means, in summary now, what we have is that B is bigger than C, is bigger than D, is bigger than A. That's the only place D could go because D has to be smaller than C, but bigger than A. Then finally, we have B bigger than D, which is compatible with the preferences we have below, and so we can put a check mark by that as well. So you see what we did was we simply enforced these inequalities one at a time as long as they didn't contradict the inequalities we've already enforced. We found that we could get all the inequalities except for the third one, and this led to this set of combined preferences. And because of that, we say that B here is the winner according to ranked pairs. This is the winner. Whoever comes in as the top choice, this is the winner according to ranked pairs. So why is the ranked pairs voting method my favorite way for determining the winner of a preferential ballot election? Well, roughly speaking, it's because it has these four properties. It's Condorcet, it's clone invariant, it's monotone, and it's last place loser independent. And of all the methods I've discussed in this video series, it's the only method that has all four of these properties. And each of these properties is just too good for me to not want to have these properties. So, also, I think it's reasonably simple. It seems complicated, but that's the nature of preferential ballot elections. When you take preferences from every single individual, you're collecting a great deal of information. And so it's important to recognize that with that great deal of information comes a harder problem of determining the winner of the election. The good news is if you go to that little extra work to determine the winner of the election, you can get a result that actually reflects the views of the voters more accurately. And these four properties are not something that a mathematician likes. They have real-world implications for the game theory of ranked pairs. And I guess if you were to say in a few words why I liked ranked pairs the most, is because ranked pairs has the best game theory. In other words, it's not that ranked pairs is beautiful, but it is beautiful mathematically, but that's not my reasoning. And it's not that ranked pairs is popular or fashionable. It's that the game theory is, in some ways, the simplest and also most in alignment with what I would say are democratic values. Okay, so let me explain that because this statement is both a math statement and also a statement about what does democracy mean to you and me. So when you look at a preferential ballot election, you have all this data of all these preferences from each voter. If we look at all the pairwise matchups, this data is important because it really is the part of the data that is beyond debate. We know that the voters prefer A over B. And so this data should be used, first of all. Secondly, the ranked pairs method is Condorcet. Now, what does that mean? It means that, let's say, so for example, that candidate B actually had all positive numbers in candidate's B row, then candidate B would win the election every single time. Now, you notice that B did not have all positive entries. B won anyway, and it's because B's one loss was taken care of by the fact that B had this larger victory and C had this larger victory. So we had to resolve this cycle of A beats B, B beats C, C beats A by looking at the components of the cycle that were the strongest, and then we had to throw out this third preference, which simply wasn't compatible with the first two. But if B beat all of the candidates, then you would have positive number, positive number, positive number, which means that B would always be on the left side here of these inequalities, which means that B could never end up anywhere other than first place. So the reason it's important to have the Condorcet property is that centrists tend to win. Centrists tend to win. And what do I mean more precisely? What I mean is the game theory for candidates running in these preferential ballot elections is to be the most centrist. And that's very, very different from our current politics using the plurality method, for example, in the United States, where you have two political parties, and each political party, neither political party is really a centrist. You have the center of the voters on the left and the center of the voters on the right, and then those two candidates go up against each other and try to be the most centrist at the very end. But the truth of the matter is that centrists can't even get the nomination of either political party, so they certainly don't tend to win. It's a very unusual thing for a centrist to win a plurality election. This clone invariance is also a very important property, and it's one reason that people like instant runoff voting is that it's clone invariant. But it's ranked pairs is clone invariant too, and so what that means is if you have a bunch of candidates that are all in the same political position, that you don't have to worry about them splitting the vote. So with the plurality method, which is not clone invariant, you've got this problem that if you have, let's say, 7 Democrats running against 1 Republican, then the Democrats would all split their vote, and then the Republican would win. Or if you had 3 Republicans running against 1 Democrat, the Republicans would all split their votes, and the Democrat would win. So this clone invariant says that's not a problem. And so what that means is you can have as many candidates running as you like. There's no need to have only one candidate from each political party. And so it also means that if you don't have to worry about spoilers as much. You don't have to worry about a candidate on the left or the right taking 5% of the vote away from a candidate who actually had a chance to win. And so in particular, this means that voters can actually vote for who they want to vote for. If you want to vote for someone who has no chance of winning, that's your first choice, fine. And you can still have your vote count in the main election between the candidates who actually have a chance of winning. And so this basically means is that you can have many candidates from each political party. If you like. You don't have to. Of course, if Republicans and Democrats still only want to nominate one candidate each, they can certainly do that. Monotonicity is also a very important property. And we talked about this in detail with instant runoff voting, because instant runoff voting does not have monotonicity. It's not monotone. And what this means is you can actually get into situations with instant runoff voting, for example, where candidate A is going to win the election, but then at the last second they go persuade a few more people to vote for him, and then because of that, candidate A now loses the election. Well, this is all awful. It's actually, how can you imagine that? It seems very anti-democratic. Certainly you'd want as many people voting for you as possible. So the fact that some voting methods do not have this monotone property makes me want to rule them out immediately. And on the other hand, ranked pairs has this monotone property, which means that voters can vote honestly. Now I should comment that I'm paraphrasing what's really true. The monotonicity property does not mean that there aren't some very unusual, rare situations where voters might want to vote dishonestly for some game theoretic reason. But these are unusual situations, and certainly if you simply rank a candidate higher on your ballot, then that will help that candidate at least. So you should roughly speaking, voters are encouraged to vote honestly because of the monotonicity property. Finally, there's the last place loser independent property of ranked pairs. Of all the methods I've discussed in this video series, the ranked pairs is the only one that has all four of these properties. There is one other method that has the top three. That's the Schulze method, and that's why I like the Schulze method quite a bit. But ranked pairs also has this fourth property that has its last place loser independent. Now, what does that mean? Well, it means that if you have whoever came in last place according to ranked pairs, which is candidate A in this case, if they were to drop out the day before the election, it would not affect the outcome of the election. Candidate B would still win. Now, why is that? Well, see how A came in last place? Well, that means that A is actually on the right side of every inequality over here that got enforced with a check mark. So A is on the left side here, but that got an X mark. And so if A were to drop out of the election, the only inequalities that A is actually involved in have A on the right side, which means that the placement of all the other candidates is not affected by where A ended up placing. So A can drop out the day before the election, and it doesn't affect the outcome of the election. Now, what would be really nice is if ranked pairs was fully loser independent. Like, it would be nice if all of the candidates, if B, C, and D, A, if all of them, any of them were to drop out, B would win no matter what. But it turns out that's impossible. It turns out there are examples where you can have candidates that didn't win the election, and if they drop out the day before the election, then that changes the winner. And that's an unfortunate thing. So loser independence is something that's not possible for any method to have. However, last place loser independence is possible to have, and ranked pairs has it. So I interpret this as ranked pairs has at least some independence from losers dropping out the day before the election, and I think that's an important property. And effectively, the implication is that fringe candidates are irrelevant. And I think that's an important property to have. You don't want some candidate who's only getting 2 or 3% of the vote to be able to extort the potential winners of the election by saying, hey, if you win, I want a government position of some kind, and if you don't, I'm going to drop out the day before the election and make it to where somebody else wins. So I think fringe candidates shouldn't have an impact on the outcome of the election, and so that's this property, last place loser independence, gives you that property. So in summary, ranked pairs has 4 really important properties that I think are important. Ranked pairs is reasonably easy to use to determine the winner of a preferential ballot election. And so for that and other reasons, ranked pairs is my favorite method for determining the winner of a preferential ballot election.